Good afternoon, everyone. I'm David Brown. I'm a professor in decision sciences at the Fuqua School of Business. I'm also faculty director of Fuqua's EDGE Center. That stands for Energy Development in the Global Environment. And I'm delighted to have the opportunity today to present some of my research related to analytics for energy systems. So if we could go ahead and please share my slides, that'd be great. Thank you very much. And one of the exciting things about working in the energy space for those interested in analytics is that the industry as a whole has long been on the forefront, the cutting edge in terms of adopting machine learning methods, optimization, AI. Despite that relative sophistication, there are many opportunities to improve the efficiency of various energy systems, and those opportunities are only growing as we look at more volatility in those systems due to climate change. And I should say, before I get rolling here, I welcome your questions in the Q&A. Feel free to drop those in the chat, and I look forward to discussing those in a few minutes. Okay, so outline for today, I'm going to spend most of the time talking about one specific paper, and there's a little QR code there for that paper. This is joint work with my colleague Jim Smith at Dartmouth. And this is really about how to make our electricity grid more efficient and more reliable. And then the last few minutes, talk about some kind of ongoing related challenges and some broader challenges that we're starting to think about. And that little artistic graphic there is courtesy of our fantastic Fuqua media relations team. Okay, so motivation is something that many people are thinking about, is that renewable energy sources are great in that they're low cost, they're clean, but they're intermittent, which creates a real operational challenge in terms of managing extra uncertainty in these systems. So this is a classic picture. This is a duck curve from California ISO. And what we're showing here is total demand for electricity net of all renewable energy supply in the state of California. And so overnight, things are pretty predictable. And then early morning, sun comes out, we get a lot of solar energy, that's great. Hopefully that persists throughout the day. And then the evening comes and the inevitable evening peak when the sun sets, people return home and whatnot. And we need to fill that gap in with other energy sources such as fossil fuel-based sources. Now the challenge here is that the depth of this belly of the duck, if you will, is uncertain and affected by vagaries in short-term weather patterns, unexpected cloud cover, temperature anomalies. So this creates an operational challenge for system operators. How do they manage all these other assets to appropriately match supply and demand of electricity over time? They're now calling these things not just duck curves, but canyon curves. Nice quote from the CEO of EPRI. I'm not going to reread the whole thing, but the key part is increasing the need right now for flexibility. And the methods that I'm going to talk about in this research are really all about flexibility. That's baked right into it. So the key research question is, can we develop an approach for handling this additional and growing uncertainty that not just improves performance related to current practice, but also is computationally viable at industry scale? And we think the answer is yes, and I'm going to talk through those methods. I want to give a shout out to a bigger team that I've been part of. This is the GRACE team, a grid that's risk aware for clean electricity. This is funded by ARPA-E, and there's a variety of people involved in this. It's been a great project to be part of. Notably, Duke Energy has provided us data, and the examples I'll be presenting today are based on Duke Energy data, so thanks to them. And thanks in particular to Team 1 of the GRACE team that developed the machine learning model that does the probabilistic forecasting of net demands. Here's a map of the Duke Energy Carolinas in Progress system. There's about 130 assets across the system, and I'll walk through this here in a second. Total demand varies quite a bit, and I'll show some data on this shortly, across day and across seasons, and it varies typically in the 10 to 30 gigawatt range. Total system capacity can more than meet this, and it's around 40 gigawatts. About 11 gigawatts of this total capacity is fixed and kind of constantly on, that's nuclear. So think of that as unadjustable. Among dispatchable resources that are flexible, it broadly breaks down into what I'll call slow start units and fast start units. And slow start units, as their names suggest, take longer to ramp up. They tend to be more, relatively costly to start up compared to their fast start counterparts, which tend to be natural gas-based peakers. But at full capacity on a per megawatt basis, the slow start units tend to be cheaper and more efficient than the fast start units. And that tension is going to be important when we talk about this problem. Duke has currently around 3 gigawatts of utility scale solar. That's growing, and of course going to grow in the coming decades. And storage is a big part of the story here in terms of the ability to time shift energy. Duke Energy currently has around 2.2 gigawatts, and this is largely pumped hydro storage. Moving forward, that will increase and be more utility scale battery storage as well. So we'll consider some experiments based on the current Duke Energy system, but also on a hypothetical future system, think 5 years, 10 years out, where solar is quadrupled and storage capacity is doubled. We made up those numbers, but those are conservative estimates of the growth of solar and storage compared to what Duke Energy is thinking about in their carbon plan as mandated by the North Carolina Utilities Commission. Okay, so here are some supply curves that give some intuition for the challenge in this problem. And so let's focus on the curve here on the left. And what I'm showing here is one tick mark for each of these generation assets, around 130 of them in the Duke Energy system. And then these are sorted from cheapest to most expensive at full capacity. So I've got cumulative production capacity on the x-axis. I've got the fuel types listed here right above that. And then the blue to green tick marks here, those are for the slow start units in the system. And then the pink to yellow are the fast start units in the system. So 11 gigawatts is nuclear, and that's basically constantly on, and think of that as free. And then up in here is where all the interesting action is happening. And what I've got for every unit, I've got a lower number, which is the cost per megawatt hour at full capacity, and then a cost per megawatt hour at startup. And what you see is a lot of these units that are cheaper, the slow start units at full capacity, tend to have relatively high startup costs compared to some of the more expensive fast start units that have higher costs at full capacity. And with a lot of the action in terms of the variation of demands happening in this range in here, this creates a real operational challenge is when certain units should be on and off, and what you should be dispatching from each unit, and so on and so forth. So that's the key kind of tension in this problem. Now, we're also going to consider some experiments with a carbon tax. We don't have a carbon tax in the United States. We may never have one. I wish we did. But we did this for two reasons. One, incorporating the effect of emissions is straightforward. And so we're doing that here with a carbon tax. Of course, we could also directly optimize emissions. Secondly, the influence of the carbon tax has the role of taking these coal-fired slow start units and shifting them down the supply curve and essentially rendering them obsolete in most plants. And that's consistent with what Duke Energy and many other utilities are thinking about, planning to retire all the coal units by 2035. Okay, so what does current practice do? And it's quite sophisticated, and this is consistent with every other utility, really. Every day, a planning problem is solved, and this is called a unit commitment problem. And I'll explain that language here more in a second. But the key is to think about the next week or so, some relatively long horizon, use a forecast of what's anticipated in terms of demand and a forecast of kind of anticipated solar production. A key that's a single point forecast. And then to think about the plan for the next day, think about what units need to be on or off and producing certain amounts to match that anticipated demand in the lowest cost way, respecting all the physical constraints of those units. Okay? And so this is a relatively big optimization problem. This is quite sophisticated. To give you a sense of scale, in the Duke Energy system, this is about 100,000 variables and constraints. So this is quite cutting edge. What they do is they take the binary variables from this optimization problem. These are telling you when certain units should be on or off at certain points across the day, and commit the slow start units to be on or off according to those binary variables from this plan. They also commit storage according to the plan based on this optimization problem. Then, as the day actually unfolds, hourly or more frequently, every 5 minutes, of course, demands may deviate. They do deviate from this forecast, and they adjust production using something called economic dispatch problems. And here, importantly, they can use fast start peaking production to fill in gaps. They can also adjust production up or down at the slow start committed units, but their on-off status needs to be consistent as prescribed by this problem. Now, importantly, despite the sophistication of this problem, it's not explicitly incorporating uncertainty. And so we want to think about what happens if we incorporate the uncertainty in some explicit way. Can that improve the performance? And that's exactly what our methods do. So here's a picture of how current practice might work, based on this. So I'm going to show data from our future system where I've quadrupled solar and doubled storage to make the results look a little more interesting and extreme, but I'll show all the results in a second. So here's a forecast for Sunday, October 27th in that system. They solve an optimization problem based on that forecast. In fact, over a full week forecast. Here is what the plan will look like. And I'll show a number of pictures that look like this in the next few minutes. So what I've got here is kind of a blue ribbon for generation units in the system. They're blue here because these are all slow start units according to this plan. Most of them are producing pretty constantly across the day. The height of each ribbon is kind of showing the production from each unit. And then in gray, this is important here, that's prescribing what's to be done with storage capacity. And so dark gray is charging. So actually early on in the day, in the early morning, we're planning to overproduce a little bit, store that extra little bit of energy, and then use that to feed that late morning peak. That's that light gray there where we're discharging some storage. And then charge a lot during the middle of the afternoon when it's anticipated that solar will be plentiful. And then you use that charged up storage capacity to feed the evening peak here. So that's all well and good. And as my co-author likes to quote Mike Tyson, plans are, everyone has a plan until you're punched in the mouth. And what could happen with the punch in the mouth would be demand might deviate. Okay. And demand really is going to not necessarily be on this black line over the next day. It could be anywhere in this kind of cloud of scenarios. So this is drawn from that Grace Team 1 machine learning model to forecast net demand. That's 250 scenarios drawn from that model. So what could happen? What could go wrong here? Imagine demands are somewhat higher than anticipated, or quite a bit larger. So here, imagine demands over the day actually look like this blue line, okay? And so what would current practice do? How would that affect things? So the punch in the mouth, if you will, is around 10 a.m. when things are 9 a.m. actually, things start to deviate. And how does current practice respond to that? Well, around 10 a.m., some fast start units are fired up to meet this excess demand. And in this scenario, which is admittedly somewhat extreme, the demands were high the rest of the day, okay? So those peakers were running most of the day. And so if you knew in advance, and I'm going to compare to what I call perfect information in several of these results here in a second, if you knew in advance at 6 a.m., and of course you don't, but if you did know the demand would look like that blue line, you could do 12.4% better than perfect information, which is about $1.7 million of operational costs. Now, what could current practice potentially have done differently is use some slow start units at this point. They're committed, some of these slow start units are basically committed to be off as prescribed by the unit commitment problem, and so that's not done. Now, it's not clear that's the right thing to do because it's not clear demand will stay high the rest of the day. You don't know that at that point, because that is a possible option. All right, so I'll come back to this picture and compare to what we do here in a second. Okay, so this is a snapshot of what I just talked about with current practice. What do we do? And it's important to emphasize that what we're proposing fits in relatively seamlessly with current operations. Of course, there will be some challenges in implementing them, but we're basically saying solve different planning problems here. And so here is, in words, what we're proposing to do and kind of the secret sauce behind our technology. And I would normally do 5 to 10 slides of math and get very excited and get into all the technical nitty gritty. So I'll just try to explain things in words, what we're doing. You can check out the paper. I'll take questions offline later about kind of specifics. But what we do is rather than ignore the uncertainty and use a point forecast, we confront the uncertainty directly. We model it all explicitly into the problem. Now, the challenge is that creates a very, very complex problem. So essentially what we do is we say, forget about it for a second. Let's leverage what's called the weakly coupled structure of this problem. And let's imagine that, in fact, Duke Energy is not an integrated system. Each plant actually can operate independently, but there are these prices for electricity in the market, and each plant is looking to operate to maximize their own profits according to those prices. And what we do is, for a sufficiently complex price model, it turns out you can get a description of the real optimal Duke Energy system with uncertainty that is basically spot on. The challenge is in tuning that price model, which was what we optimized, is that's a very complex idealized price model, but we can use any price model we want. And what we use is some simpler architecture. And this is what you do in data analytics all the time. You use some kind of predictor features of past demands, some simpler functions of past demands, and fit a model, analogous to what one would do kind of in regression. So with that, we can get kind of good approximations of the whole system. And importantly, what we get are what are called value functions. And this is the flexibility that I talked about. So the value functions describe in every point in time, given every possible demand scenario that could occur and every operational state a unit could be in, what's the value of being in different states? And what those value functions allow us to do is when we think about dispatch, we can now have forward-looking dispatch that captures kind of the future value of all our units being in different states at different points in time. And so we kind of get away from commitment entirely. We bake the uncertainty up front through this price model approximation. And then these value functions allow us to deploy things in dispatch in a more kind of efficient way. And I'll show some results here in a second. So that is in essence what we do. How well does it work? So let's come back to this October 27th, relatively high scenario. What would our methods do? 12.4% worse than perfect information is current practice. We cut about almost all of that out. We get within 0.3% of perfect information, which is about $1.65 million in savings that day alone. What did we do differently? Notice no peakers were used. Our dynamic approach actually starts up some slow start units around 11 a.m. And now that's a bit of a gamble. That was not an obvious thing that was the right thing to do, but it works out because that demand stayed high for a relatively long, persistent amount throughout the day. It's also smarter about how we use storage. Now, you might say, okay, is he cherry picking one extreme scenario? What happens in other scenarios? And what we were surprised to see is that kind of irrespective of the scenario, whether demands were high or low or relatively close to the average, we were winning in every scenario. So this is 250 scenarios drawn from that machine learning probabilistic forecasting model. Orange is current practice costs in those scenarios. Yellow is the unattainable perfect information costs. Blue, and it's hard to see, is ours. And we're basically right on top of perfect information in every scenario, which was quite surprising to us. And I like this comparison because it's saying the best forecasting model you could have, we're doing almost as well as you could if you could see into the future. And we're winning across compared to current practice in every scenario. Now, if we look at results on average, that's based on the future system, including carbon tax. Here are kind of gaps. So I'm showing percentage gap to perfect information on average. In the present system, on that day, we would cut costs by around 2.5%. In the future system, quadruple solar and double storage, around 8%. And then a future system with carbon tax, around 6%. That's a lower relative gain, but the absolute cost will be much higher. So in fact, this is a really significant improvement. Now, I want to emphasize, again, current practice is quite sophisticated. This is doing much better than a purely myopic approach with no optimization problem, no unit commitment problems. But there's nonetheless a fair amount left on the table, and we're actually covering most of that gap here. We're very close to perfect information. Now, you might say, look, is October 27th special? Not really. We ran many, many other experiments in this. In the paper, we report 8 sample days, but these were not cherry-picked. These are just 4 different seasons, a weekend and a weekday. Compared to the current system on average, in the current system, we cut costs around 2%. In the future system, a little over 5%. And if we include a carbon tax, 3.5% to 4%. And these results are fairly robust, again, across many other kind of internal experiments. Now, one thing I want to emphasize here is we're hearing a lot about AI and data analytics and data centers and the associated carbon footprint and energy usage, and rightly so. That's a big concern. This is not of that ilk. In fact, current practice takes a minute or two to optimize on our machines. We can actually optimize our kind of weakly coupled price model, getting us all our value functions and planning tools that we need. We do that in around 15 or 16 seconds. And this is on one of our computers. So surely someone like Duke Energy would have even faster computers than we do. So that's a really important point here. So this is competitive at industry scale. So that's a summary of what I talked about there. This part kind of describes kind of the overall gist behind our approach, how it works, some of the theory, and then in practice deploying this on industry scale, Duke Energy system. We're performing better and we're actually computationally faster, and we believe these improvements are going to be increasing as we increase the system's renewable storage size. Looking ahead, opportunities and challenges, things we don't incorporate. Well, our understanding is the Duke Energy system is not relatively constrained at the moment by transmission line capacity, so we're not incorporating that into our experiments or our models. We can't, and there's no real challenge for us to do that in principle. The challenge would be that we would have to have different price models potentially for every node in the network and corresponding transmission line constraints between those nodes. So we could, in principle, do that. The challenge would be it kind of ups the data analytics game in terms of maybe you have multiple price models if you have lots of nodes in the network, although we're optimistic these methods will work well there, even with simple architectures. The other aspect to this is that roughly 2/3 of the US electricity market is not like Duke Energy. It's not a vertically integrated utility. They are competitive electricity markets, typically called ISOs, independent system operators. And there, prices for electricity are basically set through day-ahead auctions. And so thinking about the planners still solve optimization problems, unit commitment problems, but there is this option, this potential for strategic behavior on behalf of the constituents within those networks. So someone like ERCOT would be a prime example of that. So adopting our methods and thinking about how our methods would be extended to those kinds of systems, in ISOs is really very important as well. More broadly, I didn't have a lot of time to get into the details, but how you manage energy storage in Duke Energy, that's the pumped hydro currently, that's really important. And storage is the name of the game looking forward. So having more solar and wind, that's only going to help you so much if you have extra storage capacity to time shift that energy. And so this is data from California, April 30th, and this is typical what you see every day there now in California. Nice article in early May in the New York Times about this. So much solar energy in California, and a lot of it has to be wasted, curtailed, because there's just not enough battery capacity to save it. But even that day, there's still a huge amount of battery capacity in California. So this is 20% of the evening's energy in California was generated, was basically through batteries, which is just a fantastic amount of energy, but we need more. And we need the ability to manage those batteries smartly more than ever. And so there are many related challenges, thinking about the adoption of electric vehicles, thinking about V2G technologies and how we can have mobile battery banks that could be, used to like shave peak load, things like that. Household batteries with virtual power plants. That's been, part of the game for a long time now, but thinking about how to smartly control and optimize those systems related to things like demand response pricing. And I think the biggest picture goal is I'm focusing here on this talk on relatively short-term operations, using analytics and techniques to be smarter there and more efficient. That's really important, of course. But cracking climate change is going to take decades. And one of the big things we have to think about is capacity of our systems. Where do we invest to increase the capacity of our systems? And so I would argue that one of the challenges there is appropriately making valuations in those long-term investments. And if you can be smarter with your day-to-day operations, that implies a better way of valuing those future investments and a more accurate way of doing so. And hopefully that will help us get to deploying the capital we need to increase these systems, the size of these systems. Great. That's all I have. There's another QR code for the specific paper. I'm about a minute or two over, but roughly on time. And now I'm happy to take questions you might have. I saw a few things in the chat there. Question from Soon Hyuk Choi, thank you. Kelly School. Given the upcoming development commercial plans for energy fusion, how would you say the optimization model and energy and stuff would change when generating costs become close to zero? I would say once we get to the point where we have infinite kind of free energy and infinite storage capacity, in some sense, the optimization becomes probably really straightforward at that point. We just always have enough energy on hand, and that's great. That's a good problem to have. But I would say we're going to be several decades off until we get to that point, right? 2050 would be great. I think China, they're thinking more 2060 for net zero. So the reality is these next few decades are crucial, and this is where we really need to be thinking about improving the efficiency of these systems. I think when we get to the point where we're net zero, we have infinite storage and infinite free energy, clean energy, we'll move on to other problems. A couple other questions here. Okay, so question from Kevin Maley on, does the energy industry have the capability to store electricity today to this magnitude? What are the options for storage today? So, I mean, the main options are pumped hydro, which is what Duke Energy uses, and batteries. And does it have the capacity? No. We need to expand our battery capacity in particular significantly. Pumped hydro is harder because you need to actually get reservoirs developed. That's much harder from an infrastructure standpoint. Batteries, of course, have tremendous challenges in terms of getting sufficient minerals to develop all these batteries. But I'm relatively optimistic that that can be scaled up significantly. You've got many companies in that space that are doing that. So those are the main pathways. And you're absolutely right, Kevin, that we're not there now, but this needs to be expanded significantly. And just to come back to the Duke Energy example, they're talking about relatively massive expansions in terms of battery storage capacity. Thank you. Some nice comments from other folks. I appreciate that. Um, So virtual power plants, I went to a talk at the Research Triangle Clean Tech Cluster a couple weeks ago, a fascinating panel. There was a representative from Duke Energy, I think someone else from New England ISO. So there's a question from Vishvender S. Talking about virtual power plants. And in a nutshell, what we're looking at there is essentially people, households, to make it concrete, have battery systems like a Tesla Powerwall, and that gives you energy, backup energy that you can use. And what happens is, a company like, for example, Duke Energy can have sign up for that customer can sign up with a plan with Duke Energy, and essentially gives Duke Energy the ability to pull from some of your battery capacity during extreme events, periods where they need a lot of extra energy. And so there's a lot of interesting challenges there, both on the optimization side, like how do you think about optimizing, control of virtual power plants. I think there are really interesting questions on the incentive side. How do we, and Duke Energy, for example, now has some kind of a pilot program for solar and battery installations, giving customers incentives for that. So how do we incentivize customers to adopt those technologies, but also how do we price that into their contracts, right? And so I think all of these things are interlinked and really interesting challenges. Um, all right, so question from Alex Surgeon. How has Duke Energy reacted to the findings, and is the team planning to work with other utilities with higher intermittent resources on their grid? I think there's a lot of interest from Duke Energy. Having said that, it's while I'm saying this fits in seamlessly with our operations, there are challenges, of course, in adopting them. I think we have some context there. We're working towards hopefully maybe a pilot program. That's very much we haven't actually had specific conversation on that, but that's something we'd love to do. I think that's ongoing work. Are we planning to work with other utilities? Absolutely. This is kind of work in progress. So we're actively thinking about commercial deployment opportunities, not just this specific work, but more broadly the GRACE team. So the short answer is yes, but that is all happening right now, and so I can't really give more specifics at the moment. But fingers crossed that in the next couple of years we'll be getting some opportunities to deploy these with Duke Energy and others. So, question from Nicholas. Nice to see you, Nicholas. Curious, how well or poorly would you say the energy sector is adopting stochastic energy prediction? Um, I'm reluctant to give a one size fit all answer there because this is such a big space. I would say, and a lot of these companies have third party vendors that are doing a lot of the things like, I guess, is like unit commitment planning and actually the forecasting models. These are all outsourced. So some of that is, a lot of it is proprietary. My sense is they're fairly sophisticated in terms of the predictive models. They use machine learning models and various kind of data analytics tools in terms of the prediction. I think the bigger challenge is, okay, now you know that there's kind of a stochastic, you have the stochastic model for demand. What do you do with that? And one of the things that's typical in the industry is uh, um, kind of putting buffers with things like ancillary services to pad yourself against some of this uncertainty. Ultimately, that is an acknowledgement of the uncertainty in the system. We view it, I think, as sort of an ad hoc way to do it. We would say try to model that uncertainty explicitly. The challenge is that's a very complex optimization problem, and that's kind of what we're trying to tackle. Um, so what are the current, so question from Jack Corey, what are the current limits to pumped hydro? What are you most excited about in battery storage? Is 2035 feasible to turn off the coal plants? So I think I touched upon some of these points a little bit. I think in terms of battery storage, it's really getting these things to be longer term storage, getting past the 2 to 4 hour range, getting these, to be able to be used over longer term periods of time. I think that's the most exciting thing. I think, biggest limit to pumped hydro is just, having the actual place to do it, basically being able to find essentially a big area of reservoir where you can actually pump the water in and store it. And that is technically very challenging. Is 2035 feasible to turn off the coal plants? I'm not sure if your question, Jack, is specifically to Duke Energy. I think it's very feasible, but there's a lot that needs to happen for that to happen in terms of, particularly to your point, increasing storage capacity is one of the big ones. Thanks, Dan. Appreciate that. His comment. Are you okay? Another question from Jack. I'm just going, and I'm happy. I just got a note. I'm happy to take a couple more questions. I know we're at 1, and I'll happy to circle back if we have to stop, and I'll take some questions offline on LinkedIn. Another question from Jack: are utilities tackling the problem of decarbonization optimization downstream as well for providing rebates to shave peak demand? Yeah. So demand response pricing is right in that area. That's exactly what Duke Energy's had some promotions on that. I don't know the specifics on that. Many others have adopted similar plans. I think thinking about how to design those plans optimally is really, really important. There are also various related kind of time of use plans and things related to if you have electric vehicle charging, basically being able to use energy from that as well. In terms of are they doing that? Yes, they are. I think Duke Energy has done some kind of forecasts, and again, I'm not an expert on these particular things that they've done in terms of their internal studies, but they've looked at sort of demand response pricing as part of their carbon plan, like 2030, 2035. I think it's important, but they're forecasting like shaving 600 megawatts off of peaks, which is significant. But when you're talking about, plus or minus 3 gigawatts, that alone is not going to solve things. So I think it's going to be part of the equation, but it's not going to be, it's not going to be sufficient to completely get us to net zero, of course. Good. So it seems like we're a bit past 1 o'clock. So I'll go ahead and stop there. If there are additional questions, I'm happy to check in with the chat or with LinkedIn shortly. Let me just wrap up on a couple points here. So thank you for joining us. Next month, LinkedIn Live will take a break, but please feel free to join my EDGE colleague, the fantastic Professor Dan Vermeer, on Wednesday, August 7th at 12:30. He's going to give a talk on the growing importance of the Arctic for the global economy. And more broadly, please consider following Fuqua on LinkedIn to be alerted to these and other events. Thank you so much.